Hello everyone and welcome back to the session. So in the previous part we saw what is etching and what are the different layers that one might need to etch, some characteristics of while to be kept in mind while selecting an etchant, and different types of etching, isotropic and isotropic, and most importantly how what is Miller indices, and which is important basically for an isotropic wet etching. And now today in this session we will see how this knowledge of Miller indices will help us in designing the proper masks, proper mask edges to get the different complicated shapes when we are dealing with anisotropic wet etching of silicon. So let's get started. So let's talk about the silicon wafer orientation. Okay, on the extreme right side if you see, it's a schematic of a silicon wafer, which is basically a circle with a small primary flat. Okay, now this primary flat is basically there to get an idea of what type of wafer do we have. It also sometimes depicts the cut of the wafer. Okay, basically what is the orientation. Okay, and most of the wafers that we will use, we will see in day to day activities, this surface will always be oriented to the 100 family of planes or 100 direction, and this primary flat, okay, and along with if there is maybe if there is some secondary flat, will give you an idea about the direction, doping, etc. So if you see on the left I have two cubes aligned to the Cartesian axis. If we see these cubes, we can say we have seen earlier while studying Miller indices that the faces of cubes are basically giving us the family of, let's say, the family of 100 planes. Okay, all the faces whatever you see are 100 family of planes. Okay, so if my wafer, if you imagine your wafer to be aligned to one of these faces, okay, then you can say my wafer which I have, it has a 100 surface because it is aligned to the 100 direction of plane. Okay, now the next thing comes, what we can talk about is the primary flat. Okay, now if you see here on the left side, my primary flat is aligned to this line, this diagonal, okay, this phase diagonal. Okay, I will call it as phase diagonal. There are two types of diagonals when we are talking about the cube. Is if you are talking about in 2D, okay, then if you join these 2 points you will get a diagonal in case of a rectangle or a square. In this case we will call it the phase diagonal. Then there is something called as the body diagonal. Okay, if you join these 2 points, let's say this is the origin and this is 1 comma 1 comma 1, then if you join these 2 points it will become the body diagonal. Similarly, if you join these 2 points, okay, then again it becomes the body diagonal. Okay, so let's say one of my the primary flat of my wafer is aligned to one of the phase diagonals. Okay, and this phase diagonal is basically nothing but the direction of 110. Okay, we'll see it in the subsequent slides how it comes to be 110, but for now let's just say that it is actually 110. And if you talk about these edges have a direction of 100. Basically we are talking in general, if we say it might be 010 or 001 or 001 bar, but in this case in general we will call them as 100 and we will call them as 110 family of directions. So we can actually represent them by this notation. Okay, because we are talking about the family and not just one direction. So if you talk about the edge, okay, this will be 100 direction. If you talk about the phase diagonal, it will be 110 direction. And if you talk about the face, any of the faces, then it will be 100 family of planes. Okay. Now if you see here, this wafer flat or the primary flat is aligned to 110 in this case, and if it is aligned to this edge, okay, my edge is what? It is 100. So here the wafer flat is aligned to 100. Now one important concept we will borrow from mathematics is the intersection of planes. Okay. Now let's say I want to find the angle between two planes. Okay, let's say if you see the figure on the extreme right bottom, let's say at the first glance it would look like you have opened a book. It looks like a book. Okay, but that's also a good analogy. If you open a book, you have basically two planes, and that's what I am talking about here. I have one plane, plane 1, okay, and plane 2. So the direction of plane 1 is represented by h1 k1 l1, and the direction or the normal of plane 2 is denoted by h2 k2 l2. Okay, and let's say these planes are intersecting at excuse me, these planes are intersecting at a line, okay, whose direction is given by the square ABC enclosed in a square bracket, and the angle between these two planes is theta. So what information can we have, can we get from these two directions h1 k1 l1 and h2 k2 l2 is, first we can find the find or calculate the angle theta between these two planes, which is given by the dot product. Okay, if you take a dot product, you will have cos theta is equal to h1 h2 plus k1 k2 plus l1 l2 divided by the magnitudes of both these directions. Okay, now from here you can get the angle theta. Okay, now same thing, if you take the cross product, you will get the direction, this direction ABC, which is basically the intersection of these two planes, will be given by this cross product formula. Okay, so let's calculate some very important angles and directions which we will be using in the subsequent slides. Okay, so I told you that there are three very important planes in silicon crystals. One is 100, then we have something called as 110, and also we have 111. Okay, let's say now since how we do, let's see if what I have here I have 111, there are no commas in between, and it is enclosed in a round bracket. That means I am talking about a plane. Okay, this is I am talking about a plane. So I have these two planes, and I want to know where do they intersect. So what I'll do here is I'll take a cross product. Okay, how do you take a cross product? Is something like this. Okay, I have 111 and 100. Okay, now to take a cross product, I'll take I 0 minus 0. Now if you expand this, again 0 minus 1, and what you get here is minus 1. So essentially what I am having here is 0 I plus j minus k. So essentially if I take only these values, what I get is 0 plus 1 and minus 1. Okay, here instead of minus I'll write a bar, and what I'm having here is a direction, right? It's a line, it's a direction, because if you intersect two lines, you get a point, and if you intersect two planes, you get a line. So this is a line or a direction. I'll enclose it in a square bracket. But if let's say I'm talking about a single plane, what if I had a family of planes? I want to know where these family of planes, different type of 111 planes intersects with different types of 100 planes. So what I'll be getting here is a family of directions which will have 10 and 2 unities. That means I'll get a direction of 110. Okay, now this is the first thing what you should keep in mind. Wherever you see that my plane my 100 plane is intersecting my 111 plane, that means definitely the direction would be a 110. Now next thing is, where does my 111 one plane intersect another 1 1 1. Okay, now here I'm talking about a single plane, but essentially what I mean is I am talking about what are the various combinations where my any of the two planes from my 1 1 1 family, okay, from my 1 1 1 family would be meeting. Okay, so if I do an ijk, if I do a cross product and just keep 1 1 right 1 1 1 repeat these two planes, basically what I'll get is 0, because if I'm talking about the same planes, basically they are coinciding. I cannot say where are they intersecting. So I'll use two different planes. Let's say I have 1 1 1, then let's say I'll have 1 1 minus 1. It is basically the same family of planes. Okay, so what I'll have here is I minus 1 minus 1 minus 1 minus 1 plus k, and here it gives me a 0. So what I have here is minus 2 I plus 2 j plus 0 k. So basically this direction what I am getting is minus 2 2 and 0, and now if I wanted to the lowest integers, I'll have minus 1 1 0. This is the direction which I am getting for these two particular planes. But if I am talking about the possibility of a combination of such planes, what I'll get is a family of 1 1 0. Okay. So here again my 1 1 1 plane is intersecting my 1 0 0 plane also at this family in this direction, family of directions, and also when my 1 1 1 plane intersects another 1 1 1 plane, that family of directions is also 1 1 0. Okay, now let's say let's use the dot product to find angles between two different planes. Okay, let's say I have my 1 0 0 and 1 1 0. It's pretty straightforward. We have cos theta is equal to if you take a dot product, what you will have is 1 into 0 1 into 1 plus 1 into 0 plus 1 into 0 sorry 0 into 0. Okay, divided by the magnitude. The magnitude of the first one is 1 square plus 0 square plus 0 square, it becomes 1 square, and again here 1 plus 1 it gives me 2. So essentially what I have is cos theta is equal to 1 by root 2, which gives me theta is equal to 45 degrees. Okay, so this is my angle between 1 0 0 and 1 1 0. And if you see in the Cartesian format also, it will be pretty straightforward and you will be getting an angle of 45 degrees only. Okay, now if you focus on the on this region where when I am talking about the angle between 1 0 0 and 1 1 1 on the right side, you will see again cos theta will be equal to, let's say what will be the dot product here, it will be again 1 divided by let's say okay, let's say this will be 1 into root 1 into 3. Basically what you will have is 1 upon root 3, and if you take cos inverse, you will get 54.73. This is the angle between a 1 0 0 and a 1 1 1 plane. And this is this might seem familiar because in one of the slides where we had not discussed about Miller indices, but rather we there was an image depicting the anisotropic etching of silicon. There this number was there, the angle was 54.73. Now let's move to another concept of etch profile. Okay, let's say I have here two identical shapes. Okay, let's say I have my silicon wafer here. Okay, just a denotion, I have a silicon wafer, and here I have a very small, okay, this is not to scale, so this is a very small opening, okay, a square opening I have here. Okay, and basically this blue region is the etch mask. Okay, this is the etch mask. So my KOH, let's say I am using KOH to etch silicon, and the white region that you see in between is the exposed silicon, and the blue region is the etch mask, let's say silicon nitride or maybe oxide, and my KOH will not affect it. Okay, let's assume that. So what will happen here in this case is, if my wafer flat here, let's say wafer flat, what you see here is 110. Okay, so this direction will also be 110, and also all these directions what you see of the whole square, or all the edges of the square will also be 110. How do we know that? Because in the previous slide we calculated that the angle between 100 and 110 direction is actually 45 degrees. Okay, so if you see on the here on the right side, I have what I have here is my 100 direction. Okay, so all these directions what you see, all the edges of this square will be actually 100 direction. Okay, now if you coming back to the left side, if you remember what is the etch stop? Okay, what is the etch stop for silicon etching is basically a 111 plane. Okay, so and where does my 111 plane actually intersect my surface? Okay, here I have the surface is 100. So what I need to essentially calculate is, where is my 100 surface intersecting the 111 plane. And if you go back to this this slide, we have here calculated that my 100 surface or plane will intersect my 111 plane at this direction 110. Okay, so here it's pretty straightforward because I already have my 110 marked out. Okay, and what I'll be getting is, we'll see how we get it, but once the etching starts, okay, my etching will finally what I'll get is something like this. Okay, the etching will start converging at an angle of 54.73. Okay, because that is the angle between my what do you say, my 111 plane and my 111 plane and 100 surface yeah. So this angle, this plane will be, if you see it from the top, it will be keep going forward in the downward direction at an angle of 54.73. Okay, and finally when the etching is stopped, right now what happens is, this is the 111 plane. Okay, so etching won't continue in this direction. Okay, but it will keep going down in the downward direction. Finally what will happen is, this etching will keep moving forward, and this square that you see will keep getting smaller and smaller, to the point where I have a pyramid shape. Okay, somewhat like this, I'll have a pyramid shape, and all these planes, 4 planes which are making this pyramid, will be 111 planes. Okay, and if you similar shape we will be getting in this second case, because it is 100, we will actually need to calculate where does my 110 direction lie, because this is the direction where like I said here, in the first case my 111 plane and my 100 surface will be intersecting. So previously we also saw the angle between this 100 and 110 plane, or the direction in this case. In both the cases it will be 45. So we will have something like this. Okay, we will have something like this at an angle of 45 degrees to this square. We will have another larger square. Okay, and finally, yeah. So we will have something similar from the first case, but the square will be a little bigger, and the reason here is because once this etching starts, my etchant will also go inside here below this mask and carry out the etching process, because there will be a gap. My etchant will start ingressing inside this cavity, and the entire part will be etched till it sees that 100 direction. And finally here also we will have a pyramidal cavity. Everything, the mechanism of reaction remains the same. The only thing is, because my mask was not aligned to the 100 direction properly, rather it was in the direction of 100 and not 110, what I will be getting is the final cavity will be a little larger, and to be precise it will be root 2 times larger or 1.414 times larger than the desired cavity. Okay. So, let us move forward. Now, this is on the right side, if you see, okay, on the right side I have 2 cubic cells, okay, and I have marked a few just 3-4 lattice points. Let us say this is 0, 0, 0, and here we have in the x, y and z direction. Okay. And if you see these 2 cubic cells, it will be a little easier for you to visualize this plane which I am talking about. Okay. The same thing I have kept it here on the left side, okay, the same thing. The only what I am trying to do here is this is 0, 0, 0, this is 0, 101, this is 101, and this becomes 0, 1, 1. Okay, and I am not actually these are points, so I will show them by commas and a bracket. Okay, now tell me what would be this line. If you remember the Miller indices of directions, the idea was to subtract the tail coordinates from the head coordinates. So, this gave us the direction of 101, but this 101 is basically the family of 110. Okay, and similarly here also what you will get is the family of 110. Okay. And if you talk about this line, you see this line, okay, this line is also the family of 110. How do we get it is we can always do the subtract the tail and head coordinates and see the direction. Let's do it here quickly. Let's say let's take any one of the points. Let's say 101 and subtract 011. If you subtract this, what you will get is here is 1 minus 1 0, which is essentially the same as this family of plane 110. Okay, and also previously what we saw, we are proving it here that this top face, what I am talking about, this top face is basically 100. Okay, and this plane what I am talking about here is basically my 111 plane, where my etching is actually going to stop. And how do I know that this is my 111 plane is because if you see here, if you connect these 3 points, okay, if you connect this point to this point and this point to this point and these 3 points, you get something like a triangle. Okay, and previously we saw by connecting these 3 points, the triangular region that we are getting is basically a 111 plane. Okay, so that's now that is that we can see that these were the 2 111 planes, and where these 2 111 planes are intersecting, basically again if you do a if you see this head and tail coordinates, we can clearly see that this direction is 110. Okay, and where this 111 plane is actually intersecting my 100 phase is also this 110 direction. Okay, now that is clear. If we let's see the figure below. Okay, in this figure also everything remains the same. The only thing is that the cross section which I am taking is a little different. So, if you see this smaller square, this smaller triangle, okay, basically it is a cutout piece from the larger triangle, okay, a larger 111 plane. I have made a cross section. So, what happens here essentially is here if I am seeing what I am in the first figure, in the top figure, what I am seeing here is if I observe from this portion, this region or this angle, what I am seeing here is not actually the cross section of the 111 plane, but I am seeing 2 110 lines here. Okay, okay. And but when I take a cross section along this line, and if I see from this angle, what I am essentially seeing is a cross section of the 111 plane. Okay, these are two different things. Okay, if you see here, what from this angle what I am observing is a cross section of the 111 plane. Okay, and from if here what I am seeing is in this region what I am seeing is actually two 110 lines. Okay, we will see in the next slide how does it matter, how does it affect your calculations. Okay, let us see here. Okay, now on the right side I have, if you observe here I have my surface is definitely still 100. Okay, in both the cases my silicon surface is 100, but the mask edge here it is aligned to 110, and here it is the mask edge is again aligned to 110. How do I know that? Because this is at a angle of 45 degree with 110. Okay, so what I and this mask, both the masks are identically the same, both have this what do you say an edge length of A. In both the cases there is an edge length of A, and mask edge is aligned to my 110 direction. So essentially if you consider the physics, okay, if the mask edge is aligned to 110 direction and the edge length is same, essentially whatever shape you get should be one and the same, and I will prove how that it is actually same, but depending upon from which angle or cross section you are viewing, the calculations might differ a little bit. Okay, so let us say in the first case it is quite clear that here if you see this was my 111 plane. Okay, and if I cut it from here, basically what I am having is a cross section of my 111 plane. So here if you see this angle, okay, this angle comes out to be the angle between 100, because this direction is this plane is actually 100, and this plane what I am having here is 111. So the angle between this comes out to be 54.74 or 54.73 rounding off. So if I want to calculate the ratio between these two things, okay, let us say this because this was A, this entire length was A, and this becomes A by 2, and if I want to calculate the value of x, okay, I will take a tan of x upon A by 2, and I know that this value comes out to be x upon A comes out to be 0.707. Okay, and on the right side if you see, okay, again the mask is remaining the same, only the cross section, the cross section instead of having a cross section along the what do you say along the edges, I am having a cross section along the diagonal. So how does it matter? First thing that changes is here what I was having was A by 2, but here what I will have is A by root 2, and this in this cross section what I see here is if this is A, this entire thing becomes root 2A, and here what I have is A by root 2. Okay, and again if you carefully observe this cross section, what I am having is actually what I am seeing is an angle between two 110 lines. Okay, and the this so basically this is my direction 110, this is also my direction 110. Here if you don't get confused here what I was seeing was a 111 plane, because I am representing it by a curly bracket. Here what I am having is a direction represented by a square bracket. Now the direction and this direction is also 100. Okay, so the angle between 110 and 100 we have already calculated is 45 degree. So we take a tan of 45, and finally we end up with this solution where x upon A turns out to be 0.707. and if you compare these two sides, okay, left hand solution and right hand solution, we see that the if my edge length is A, okay, and my mask edge is aligned to let us say 110, okay, no matter what cross section I am seeing, the x upon A, basically the depth to the mask edge length ratio remains the same. Okay, now keeping that in mind, let's have a quick problem here. It's a little interesting because we are having something, we are not just what do you say, etching away from the surface, but rather there is a pit. Okay, so let's focus on the figure on the left hand side. So let's say here it's basically a groove, and my etchant is coming from the top. Okay, so what will happen is my etchant will ingress from this cavity here. Okay, and it will start etching on the sides. Okay, let's say on the right side it is etching. It will stop when it sees a 111 plane. Okay, but it is also going on the top. Here it sees a 100 plane and it starts etching everywhere. So it will stop when it sees another 111 plane. Okay, here. So basically I'll have a cavity on the right side. What I see, same thing will be repeated on the left side. So I'll have this kind of shape. Okay, I'll have this kind of shape which will be confined by 111 planes. Okay, so if you come here, this is the kind of cavity. If there is a hole, this is the kind of cavity you will get, and this angle theta. Okay, this angle theta would be either, it can be, let's say we remember depending upon what was the which cross section we are viewing, it can be either 45 degree or it can be 54.73 or 74 degrees. Okay, okay, let's say or. Okay, now let's say this this cross section what I am viewing. Okay, this here is 110 direction. Okay, this direction is 110. Let's say this, I'll denote it by this because I am talking about a single direction. Okay, if this is 100, if you quickly go back, what do you see here is, if it is 100, what I'll get is 54.74. Okay, so this, okay, sorry, so this angle here, if this is 100, this theta what I'm seeing is 54.73 degrees. Okay, so in that case what happens is my if you remember again, if this is 54.73, then the this tan of 54.73 or let's say 74 actually is under root 2. Okay, so if I take a tan of theta, which is basically what I am having here is 5 microns, here you can see it is 5 microns divided by this region. Okay, let's say this is x. Okay, which it is actually equal to root 2. So my x what I'll be having is equal to 5 upon root 2. Okay, and it basically turns out to be 10 root 2 by 2. So it turns out to be somewhere around 3.53 microns. Okay, and similarly, if in the other case, let's say this direction was actually 100. Okay, in that case this theta would be 45 degrees. Okay, so in that case it is pretty straightforward. Tan theta would be equal to my let's say this for theta is 45 degree, so my tan theta would be, this is 5 microns divided by x, which is actually equal to 1. So my x turns out to be 1 micron. Sorry, my x turns out to be 5 microns, not 1 micron. So so this is pretty much everything. If I combine these two, if I look at it again, so if this direction is 100, my and the depth here is 5 micron. So if depending upon the cross section from where I am viewing, so here in this case the x will be 5 micron. In the previous, if this direction was, cross section was along 110 direction, my value of x would be 3.53 microns. And I would request you to try this one problem what I have on the right side. Okay, try this problem and see what you get. In both the cases, in one case the direction should be 100 and in another case the direction can be 110, and let's see what you basically get when you take these two cases, case A and case B, and try this solution. So that's pretty much everything what I had to talk about. And so just to have a quick summary is we started with we started with what is etching, the types of etching, wet, dry, azeotropic and isotropic, what is the criteria for selecting an etchant, and why an isotropic wet etching is a little counterintuitive, or why it is complicated, and how the knowledge of Miller indices and crystal planes can help us in finding out in designing very complicated microstructures, and what is the mathematics behind them. So with this we stop here. Thank you.